It's a pleasure for me to introduce the Professor Lorenzo Liverani. Professor Lorenzo Liverani completed his PhD in the Politecnico de Milano in 2023. He has a good scientific production, publishing 16 articles in high impact journal. He is currently part of Friedrich Alexander University as an Alexander von Humboldt postdoctoral researcher. In this occasion, he will give the lecture entitled Stability of Hyperbolic System with Non-Symmetric Relaxation. Welcome, Professor Liverani, and you can start.
Thank you very much. Thank you. And please let me know if you can hear everything. So I will try to be as clear as possible. So yeah, let me hide this thing here. All right. So today's talk will be about a recent paper I wrote in collaboration with Timothée Krembara, Lingyun Xu, and Professor Enrique Zozua, who is my current, let's say, supervisor at the FAU University. And this paper here is about the large time asymptotics for systems of hyperbolic partial differential equations. So the general framework is that we have a system of equations who has a solution which exists for all times, and we want to know what happens as time goes to infinity to this solution. All right. So does the solution decay to zero, or does something else happen? Okay. And so this is the main question that I'm trying to answer today. And the problem is that in this setting here, the theory becomes very technical very quickly. Okay, so we'll try to keep it as hand-wavy as possible because I want to basically. So, well, first of all, I want to make you understand what kind of results we proved in this paper, but I also want to make you understand with this talk that the techniques I'm going to discuss today are quite general, and they can be seen as tools. Okay, so it's not just the abstract result that I'm going to tell you about, but it's really the way of dealing with these kind of systems that might be interesting to some of you listening. Okay, so okay, and precisely to be and wavy and not to be too technical, I have tried to structure this talk in a video game fashion. Okay, so you will follow me trying to solve some levels that I've prepared of increasing difficulty. And hopefully at the end of the talk, you will have a general idea on how to apply our tools and the tools I described in this paper. So the video game I have created for you today has a very bad title, I realize, okay? But the title is, Does the energy of the system of hyperbolic PDEs decay? Okay, and yes, it's very bad, it's very long, but at least it contains the three main actors that will play a role today. Okay, so we have a system of hyperbolic PDEs, and this will be clear in a second what is the main structure of systems of this kind. And to this system, we will associate an energy, which will be, as we will see, just the norm, a suitable norm of the solution. And finally, we want to know whether this energy decays as time goes to infinity. Okay, so we want to devise techniques to show that this energy decays. And as in every video game, the first level is always a tutorial. So the idea of the first level will be to just establish which are the rules by which we can play. Okay, and on a very simple example, actually the easiest example you can think about. In this case, we don't even have a system, we have an equation, which is just an equation in one variable. And as you can see, it's a partial differential equation, right? So we have the partial derivative in time plus partial derivative in space plus u equal to 0. And in this case, it will be crucial during the talk that x belongs to R. Okay, so it has to, the spatial space has to be unbounded, okay, and it's the whole real line. We don't have boundary conditions in this case. All right, so as I was mentioning, we have an equation, and to this equation we associate an energy, E of t. No. Okay, well, so, all right, okay, I will go on with the presentation then. Right.
Please, Lorenzo.
Yes, I have started to record also on my computer. So if there's any problems, we can just go on with my registration. All right, so sorry for the interruption. As I was saying, let me go back. So as I was saying, we were studying the tutorial. Okay, so let's go back to the presentation. We were studying this very simple equation, and as I said, the energy of the system is the L2 norm of the solution. So whenever you see this norm here today, it will be the L2 norm of the solution. And the question that we want to answer is whether this energy decays as time goes to infinity. Now, there are several different ways of showing whether the energy decays. But in this case, I will use, along this talk, I will use my favorite method, which is the multiplier technique. Okay, so what you do is basically you take your equation and you want to multiply your equation by a certain combination of the variables at play. In this case, we only have one variable, so we just take the equation and multiply the equation by u in L2. Okay, and what you get is obviously a sum of three terms. Okay, so you get three scalar products in L2. The first one you can show quite easily simply the derivative of the energy in time, okay, times 1/2. The second term is actually 0. And here it's very important that x belongs to R, okay, because not having boundary conditions implies that this term is actually equal to 0. And finally, you have the scalar product of u against itself, which is the norm of u in L2. But this is actually the energy. Okay, so in the end, you end up with this kind of equality here, that the derivative in terms of the energy plus twice the energy is equal to 0. And this, by the Cronval inequality, in this case is even an equality, okay, shows that the energy decays exponentially fast as time goes to infinity, okay, completing the first level. So these are the main rules, okay? We will be given an equation and we want to use the multiplier technique to show that the energy decays. Let's check a bit of a more complicated example, okay? So in this case, we actually have a system of equations and in two variables. So the energy will be the sum of the two norms of these two variables. And as you can see, u1, the first variable, is coupled to u2 with this term here, where the x derivative appears, okay? Now, again, we want to know whether this energy decays, and naively, what we can do at the very beginning is to just do the same multiplication we did before, okay? So before, we multiplied the equation by the variable present in the equation, okay? And here we do the same. So we multiply the first equation by u1 and second equation by u2. You do a lot of computations here. Well, not a lot in this case, but you do some computations here. And what you discover is that after this multiplication, you end up with an equality relating the derivative in time of the energy plus the L2 norm of u1 equal to 0. And this seems nice because it's very similar to the previous equality that we got in the previous level, okay? But in this case here, now this is not complete, right? Because the energy is the sum of two components, and we only got one component here. So we would really like to have also u2 squared, okay? Now, to obtain the u2 squared, what you want to do, the general strategy usually, is you look at the norm that you recovered, in this case u1, you go to the equation for u1, and then you multiply by something giving a norm of u2. So in this case, we cannot multiply by u2, simply by u2, because then we would get u2x scalar product u2, which is equal to 0. So what we do is we multiply by u2x, the first equation, okay? And only the first equation, okay, in this case. So, okay, now there is some computations to be made, and but luckily you can ignore the computations. These are here only for those of you who are familiar with this kind of techniques. Okay, those of you who don't know the multiplier method can only focus on the last inequality. Okay, so what we get at the end of this chain of computation is an inequality showing that the derivative in time of a scalar product minus a term containing the derivative, minus a term containing the norm of u1 plus a term containing the norm of u2 is smaller than or equal to 0. So let's recap very quickly. What we obtained was these two relations, okay? That the derivative of the energy plus u1 squared is equal to 0, and this second inequality here. Now, what we would like to do is to put these two together, okay? Because if we are able to sum them up in a clever way, then we obtain norm of u1 squared plus norm of u2 squared, which is the energy. Or let's say it's not really the energy, right? Because as you know, the energy does not have an x derivative inside of the norm. So this is actually a problem. We need to find a way to deal with the fact that here an x derivative appears. And okay, so at the beginning I said I will try to be non-technical in this talk, but you have to allow me to show you just once what is one of the techniques that one can use, which is that you can pass to the frequency space. And so take the Fourier transform of all the variables at play. And then by Plancherel theorem, what you get is that these relations here are translated into the frequency space. And this is very interesting, very important actually, because now the x derivative in the frequency space simply becomes a weight. Okay, it's a frequency dependent weight, this xi squared divided by 2, but it's still a weight. Okay, and the energy now is simply u1 squared plus u2 squared. So provided you can multiply the second equation by a suitable weight, okay, then you can sum these two up and you can obtain the decay of the energy. Let me show you how it's done usually for this kind of problems. So you have these two relations here now in Fourier space. And what you do is you define the Lyapunov functional here. This is called L, which is simply the sum of a term containing the energy, this first term here, plus a perturbation, which is epsilon times a coefficient which depends on the frequency, times the scalar product that appears here. Okay, this is just rescaled. I brought this xi outside of the scalar product. Okay. So if you define this functional here, then what you can show is that, first of all, this Lyapunov functional here is equivalent to the energy, because if epsilon is small enough, then this is simply the energy plus a perturbation. And secondly, by summing these two relations together, you find that the derivative in time of this function plus the functional itself times a certain constant, which might depend on the frequency, is smaller than or equal to 0. So at this point, you can use the Gromval inequality to show that L decays, and this entails also the decay of the energy. Okay. In particular, what you can show is that the energy decays exponentially fast in high frequencies and polynomially fast in low frequencies for this system here. Okay. And so this completes level 2. All right. So this should give you a very rough idea of the systems we are going to deal with. And now I would say we are ready to see a slightly more complicated example. Okay. Now, this is a slightly harder system that we're gonna focus on in level 3. Okay, and you are probably thinking right now that this does not look slightly harder. This looks much harder than what we studied just now. But I will try to convince you that this is actually now actually quite simple to deal with. Once you know the general strategy, okay, this system will be quite simple. Okay, so before getting into the analytical treatment, just let me tell you that so you will notice that here the only terms without derivatives are these u1 appearing in the equation for u1, u2 in the equation for u2, and u8 in the equation for u8. All of the other terms are coupling, and they appear with a derivative. Okay, this will be very important. So how to deal with this system? Well, luckily, we can use the theory developed by my supervisor, Professor Enrique Zozua, and his collaborator, Karim Bochard, around 2010, 2011. Okay. So Zozua and Bochard noticed that there is a structure in the way we multiply the equations as we did before, okay, to obtain the decay of the energy. And so what they said is, let's just rewrite the system, the huge system in 10 variables that we saw just now, in vector form. Okay, so we define U to be the vector of variables. A now, here you have to believe me, okay, but if you go back to the previous system, you can check that the x derivatives are simply a multiplication by a symmetric matrix for U. Okay, so you define this A, which is a symmetric matrix, then you have Ux. And finally, the terms without the derivative are modeled by this term Bu, okay, where B is also a symmetric matrix. And with respect to A, B also has an additional property, which is that B is hypocoercive. Now, this is not really a correct word. You generally don't say that a matrix is hypocoercive, but I think this gives the idea of the property of B, which is that B is a semi-definite positive matrix, okay? But crucially, it is coercive in the following way. on some of the components of U. Not all of the components, but some of the components. So we will indicate these components by this big X. Okay, in this case, you can show that these are U1, U2, U8. Okay, and this means to be hypocoercive. Okay, so we have dissipation only on some variables, but not on all the variables. And we want to recover dissipation for all of the variables. All right, so this is the general setting that Bouchard and Zotua studied. And what they were able to show is the following theorem. So if A and B satisfy the celebrated Kalman-Rank condition, which is a famous condition in control theory, then the energy of the system decays exponentially in high frequencies and polynomially in low frequencies. Okay, precisely as it happened in level 2. Okay. Now, the Kalman-Rank condition, for those of you who don't know it, is this algebraic condition here. You're asking that the rank of a very big matrix that you build by concatenating together matrices, okay, so products of the following form, b to the b times a to a certain power, has to be equal to n. Okay, so if the rank of this matrix here is equal to n, then you have the decay of the energy. How do they show that the energy decay? Because this is the part most interesting for me, okay? So they were actually able to build a Lyapunov functional for the system and to build it in an iterative way. So you don't really need to know the system, okay? You just need to know that if you do certain steps in an algorithmic fashion, in the end, you will get a Lyapunov function. So let me show you how they did, okay? You start with the system written in vector form. And the first thing you do is you multiply this equation here by U, okay, in L2. And what you obtain is something very similar to what we just saw. So you obtain that the first term will give you the derivative of the energy times 1/2. The second term, AUX times U, scalar product, is actually equal to 0. Okay, this follows from the fact that A is a symmetric matrix. So this is actually equal to 0. And finally, the third term can be dealt with by remembering that B is hypocoercive. Okay, so BUU is actually greater than or equal to K times X squared. Okay, so in the end, what you find is that the derivative of the energy plus some of the components of U is smaller than or equal to 0, which is exactly, for instance, what we find in level 2. Okay, so the derivative of the energy there plus only U1 was equal to 0. Okay, we were missing U2, and in this case, we're missing 7 other components. All right, so this is the first step. Now, for the second step, this will be quite strange at first. Okay, so you will have to stay with me on this and just trust me. Let's consider this scalar product here. Okay, so this is the scalar product of BU against BAUX. And now we take the time derivative of the scalar product. Again, you get a bunch of computation you don't care about right now. What you care is only the final computation and actually only the red term. Okay, so what you find is that if you take the time derivative of the scalar product, then you recover the norm of BAUX squared. Okay, you can take this norm and bring it to the left-hand side. All right, so we'll say, what about it? Okay, why should I care about recovering this norm here? Well, let me show you the second step. Okay, the second step is to consider another scalar product, which is the same as before, except now instead of U, I have AU. Okay, so I have BAU against BAUX. Okay. What happens? Well, if you do all of the computation, at the end, you will recover the norm of BA squared UX. And now probably you can start seeing where I'm going with this. Okay, so if you iterate this procedure for n-1 time, at the end, you will and you sum them all together. And I'm skipping a lot here because you should define some suitable weights, but this can be done. You have to trust me. You have to trust the paper by Bouchard and Zotua at least. So what you find is that at the end, you will recover a norm of this form. Okay, so it's the sum of the first components x squared plus BAU squared, BA squared U squared, plus and so on and so forth. Okay, and now crucially, if the Kalman-Rank condition holds, then this norm here is equivalent to the L2 norm of U. So we have recovered the energy. Okay, the L2 norm of U was the energy. So if you iterate this procedure n-1 times, you are ensured to recover the norm of the energy. Okay, and which is I don't know, very, very interesting to me. Okay, that's you can do something like this because you start with a system which is very complicated, but doing some very precise steps that you can plug inside of a computer. Okay, so you don't need to actually do the computation yourself, you can find this diagonal functional. So the final diagonal functional looks like this, right? So you have the sum of a term containing the energy plus a certain, let's say, weight, which depends on the frequency, because you have to distinguish between low frequencies and high frequencies, times this sum here. And here you can really see the kind of iterative procedure I was telling you about, right? So every scalar product is always product of the previous term, BAK to the minus 1 U, times BAKU. Okay, so this is the diagonal function. All right, so this actually solves the problem for the systems with A and B symmetric, okay? Let's take a look again at the slightly harder system. Now you understand why it's slightly harder, because even though the computations here might be difficult to do by hand, conceptually, there is nothing different than level 2, okay? You start by multiplying everything by U, and this will recover the norm of U1, U2, and U8, okay? The next step will be to go in the equations for U1, U2, and U8, multiply by whatever you are coupled with, so in this case U3, U5, and U9, and this will recover U3, the norms of U3, U5, and U9. Okay, then the next step, you take, say, U3, you go to the equation for U3, and you want to multiply by U4. Okay, but instead of thinking of this, you can just see that if you now look at the next scalar product, this is done automatically. Okay, so this new scalar product is simply U3 times U4x, U5 times U6x, and so on and so forth. Okay, and you proceed. Okay, technically you should proceed up to n minus 1, where n is the number of variables. So we should get up to BA to the power 9. But in this case, we recover all of the norms just in 3 steps. Okay. And this actually completes the level, because at the end, you know that the energy of this very complicated system here decays exponentially fast in high frequencies and polynomially fast in low frequencies. Okay, as the theorem said. All right, very well. So now you are in position to understand what was the result that we studied in our talk, in our paper. Okay, so what we did was to study the setting in which the matrix B now is no longer symmetric. Okay. Why should we study something like this? Well, because actually, even though the result of Bochard and Zozua is very interesting, okay, when you go into physics applications, you find a problem, which is that most systems in physics actually have B that is non-symmetric. And the reason is that a variable can be coupled to another one in 2 different ways when you look at hyperbolic systems. So you can have the usual coupling that we are used to in this talk, where an x derivative appears. So you have that U1 is coupled to U2 by this U2x, U1x. But also you can have a coupling which does not involve derivatives. Okay, so U2 is coupled with U3 in a way that does not involve derivatives. Okay, and this minus 2 in the end up in the matrix B. Okay, so you really want to be able to deal with this kind of case. Okay, and luckily, thanks to linear algebra, if you have a non-symmetric matrix, what you can do is you can divide it into a symmetric and a skew-symmetric part. Okay, so in the end, our general abstract setting is the following. So with respect to the paper of Bochard and Zozua, we have an equation that contains now 3 terms outside of the time derivative, of course. We have AUX, which is the same as before, plus BAU, plus BSU. Now, BA, okay, is a matrix that, as I said, models a coupling between the variables. So in a sense, BA is more related to A than to B. Okay, so this is, you have to think of this term as if it was just one term, okay, which models the coupling between the variables. And then we have BSU, which models the relaxation, okay, and this plays the same role as BU in the paper of Bochard and Zozua, okay, and indeed, what we ask in our paper is that BS is hypocoercive in some of the variables. It's obviously symmetric by construction, but it also has to be hypocoercive. All right, so what we showed, as you maybe can expect now, is that if a certain Kalman-Rank condition is satisfied, then you obtain the decay of the energy. Okay, so if A, BA, and BS satisfy what we call the inhomogeneous Kalman-Rank condition, then the energy of this system decays at least polynomially as time goes to infinity. What is the inhomogeneous Kalman-Rank condition? Well, it's the same as before, but now it's written in frequency space. Because now we cannot decouple the role of A and BA. As I said, AUX and BAU are basically the same term. Okay, so you have to collect them together. And since you don't want derivatives going around, you just pass to the frequency space and you say, actually, I can consider them as his own matrix in the frequency space, which is simply IXI A plus BA. So if BS and this matrix here satisfy this Kalman-Rank condition, which has to hold for every Xi belonging, for every frequency, okay, then you have the decay of the energy. And as you may expect, okay, the proof of this theorem is actually very similar to the proof in the Bouchard and Tuatua paper. Okay, so it's not as easy because you need to deal with this kind of inhomogeneity, okay? But the main, let's say, idea works the same. So you can define a Lyapunov functional in the same way I described before. So you see these iterative structures again, right? So you have that this matrix here to the power k minus 1 times this matrix here to the power k. And once you define this Lyapunov function, you can proceed in doing all of the computation to show that in the end, you will recover a norm, okay? Now, unfortunately, here there is a crucial problem that arises, which is here, right? So what I'm saying is that the energy decays at least polynomially, but this is not very precise and not very nice to read in a paper, okay? Why do I say at least polynomially? Well, remember what we saw before, okay? Why the Kalman-Rank condition was useful in the paper of Bouchard and Zotua. It was useful because at the end, you had to recover a certain sum of norms, okay? And this sum of norm was equivalent to the original L2 norm, okay? Here you get something similar, okay? But the sum of norms is inherently inhomogeneous, so it depends on the frequency, okay? And the most we could do was to show that this sum of norm is actually equivalent to 1 divided by xi to the power 2 alpha times u squared, okay? And this alpha here, crucially, cannot be quantified, or at least, let's say, I don't have the linear algebra knowledge to quantify this alpha here. So if some of you knows or has some ideas on how to do it, I would be very interested of knowing it. But in general, you can only say that alpha exists such that you have this kind of equivalence here. And this, in the end, when you get at the very bottom of the computation, tells you that the energy can decay at least polynomially, but you don't know with what decay rate. Okay, and this is quite a problem because in physics you want to know the decay rate of the energy. This can be helpful for any application, for instance, in stabilization, control theory, and so on. Okay, so what we did was to not just stop at this result, but we provide a second result, which is actually an algorithm, okay, to be able to quantify this alpha here, okay? Now, actually, before showing you this, let me go back very quickly to the Lyapunov function. Why is there a problem, okay, with quantifying this alpha? Well, at least philosophically, the reason is that this Lyapunov function here is unnecessarily complicated, okay? So think about it. Like if k, for instance, is 3, okay, then this term here is a cube, okay, of a sum, so it's 4 terms. This term here is 3 terms because it's a square. So this is 12 terms, okay? And this is only if k is equal to 3, which happens if, for instance, you have a 4x4 system, okay? The Timoshenko system, for those of you who study this kind of things, okay? So obviously, it cannot be this complicated to show that the energy decays, okay? And this obviously is just a rough reason of why we cannot quantify this alpha, okay? But it gives you an idea. And so we said, okay, let's simplify the Lyapunov function, okay? And let's go back to the strategy that we were using before to obtain the Lyapunov function, right? And if you recall, the strategy was always something like this. You always start by multiplying your system by all of the variables, right? So first equation by u1, second equation by u2, third equation by u3. And what this gives you is the decay of a certain subset of norms, okay? In the case of this system, if you do it, you will get the decay of u1, okay? So you will recover the norm of u1 doing this kind of procedure. Very well. So then we go to the equation for U1. We check the variable U1 is connected to, in this case, U2, and you multiply this equation by U2. Okay, now the coupling here, crucially, appears with appears with an x derivative. Okay, so since the matrix A was the one modeling the x derivatives, what you can show is that multiplying the first equation by U2x actually, is equivalent as doing this scalar product here, BSU, BSAUX. Okay, so you don't need to introduce all of the possible, let's say, scalar products as the Lyapunov functional was doing. Okay, you just need to use this scalar product here. Okay, so this recovers the norm of U2. Then you go to the equation for U2. You check what U2 is coupled with. And then you say, it's coupled to U3, but without a derivative in this case. What is modeling the coupling without a derivative? It's the matrix BA. So now what you want to do is you want to consider the previous term, BAUX, which was BAU in this case, which is U2, times BSA BAU, okay, which will give you the scalar product U2, U3. This seems unreasonably complicated, and I agree, okay? This is a system very simple, 3 by 3, okay? But you have to imagine that now you can do this in an abstract way for every system you want, okay? It can be a 100 by 100 system, okay? This procedure you can always do. So at step 0, you take the derivative of the energy. At step 1, you go in either A or BA direction, depending on where you recover dissipation. And the same you do at step K, okay? So you always go either on A or BA, depending on what variable you want to recover, okay? And if you do this procedure, then the final informal theorem is that you can quantify the famous alpha I was telling you about before, okay? So since now everything is explicit, okay, not only do you recover the whole norm, but you know exactly how this norm is built up, okay? And in the end, this will give you the at least an estimate on what is the decay rate, okay? And actually this estimate is, at least in all of our example, was the optimal one, but this is something that we will have to prove in future works, okay? So this is what the algorithm does. And if you apply it to this very simple system, you will find that the decay is polynomial in high frequency and polynomial in low frequencies. Okay, so this actually completes the fourth level. Now, we're almost done. Unfortunately, while we were writing this paper, we noticed that things are not as easy in the non-symmetric case. Because as you can see here, now this system is very simple, right? So U1 is coupled to U2, U2 is coupled to U3. But what could happen, and what happens in practice, okay, in several physical systems, is that sometimes U1, okay, your first variable, or I mean any variable, is not just coupled to one variable, it's coupled to several variables. And most importantly, sometimes it's coupled with different ways to different variables. So U1 is coupled in this case, for this system here, is coupled to U2 with an x derivative, and with U3 without an x derivative. Okay, so both A and BA play a role here in the first equation. And applying the algorithm naively, as I told you before, doesn't work in this case. Okay, so we needed something more. And as I said, okay, so this is actually something that happens. Okay, so this happens, for instance, in the Timoshenko system, which is one of the most studied hyperbolic systems. You have that the first variable is coupled to the second and third one. Okay, so it's something that you have to know how to deal with. And obviously, you could apply the general theorem with the inhomogeneous Kalman-Rank condition in this case. So that always works. As long as you can show that the Kalman-Rank condition holds, that theorem holds. But in physical system, as I said, you want to be able to quantify the decay rate. Okay, so you want to be able to apply the algorithm also in this case here. Okay. So how do we do it? Well, the first naive idea is since both A and BA play a role, let's just take the first equation and multiply by A and BA, okay? And then we sum the two up together. What do we obtain? Well, in this case, if you do all of the computation, you will find that you actually recover a norm, okay? But it's the norm of the sum of U2 and U3. And we would like the opposite. We would like the sum of the norms. Okay, so this is not enough. You cannot just multiply by BA and, BSA and BSBA. You need to make up some ideas, okay? And the idea was the following. So if you check what you recovered, okay, you will notice that we actually have the sum of the norm, but obviously if you develop the norm of the sum, you will get also a scalar product. Okay, so what we want to do is we want to perform an additional multiplication to one of the equations of the system to delete this scalar product here. Okay, so you want to cancel it out, because once you cancel it out, then you get the sum of the norms. So what is this multiplication? Obviously, I mean, you look at the system and maybe you could guess it. Okay, in this case is you want to multiply the third equation by u2. Okay, just for those of you interested, okay, in this. But the problem is that, as you saw up to now, what we want to do is we want to develop an algorithm that you can use for any system, okay? So it cannot be related to a single system. So what is the right scalar product to use in the abstract case? Well, the right scalar product is what we informally call the magic function, okay? We call it magic function because we could not believe this was working in every case, okay, when we understood that this was the right scalar product. Okay, so it looks something like this. So it's at least at the first for the first equation is BSAU times BSBAAU. Okay, so it seems a bit random. Actually, if you go read the paper, this kind of structure appears quite naturally once you start doing all of the computations for the previous two scalar products. Okay, but I don't want to get into the details. In front of it, you have a certain constant, which is 2m, and you can tune the m to exactly delete the scalar product that you wanted to delete. Okay, so this is the function that you have to have, and I understand this is all very and wavy, okay, but this is more or less how it works. So this actually completes the level for the system here. You can show that you have polynomial decay both in high frequencies and in low frequencies. And so just to summarize, the general algorithm that works for every system now is that if you want to recover the norm of a term which appears with a derivative, you need to do a multiplication by a. Okay, so you take the previous term, bsxk minus 1u, times next term is bsxk minus 1 au, okay, with x. If you want to recover the normal term without the derivative, you do the same, but with BA. And if you want to recover both, then you have to do both A, BA, and then sum the magic function to delete the scalar product. Okay. So it's a bit like working with Legos, basically. You want to build your Lyapunov functionals, and you have different blocks that you can add together to obtain the final Lyapunov function. And what I want to stress is that this kind of procedure is an algorithm. Okay, so you don't need to think about what system you have. Actually, what I'm doing right now, and I'm almost finished, unfortunately, I couldn't not do it for this talk, but I'm writing the program on Python to just feed an hyperbolic system of PDEs, and this program returns the Lyapunov function with all of the computations also. So you don't even need to check the computations. Obviously, something I'm glossing over is that you should devise suitable weights to sum all of these blocks. But for this, I will refer to the paper. Okay, this is a quite difficult issue. Okay, but we are able to still solve it. All right. So to conclude the talk, I should be on time. Given an hyperbolic system, we first provide a very general result for which, if the inhomogeneous Kalman-Reck condition holds, you find the decay of the energy, and this can be applied anytime. And then what we do is to provide a general algorithm which estimates the decay rates of your system. Actually, a third result I didn't tell you about for time reasons is that this algorithm is able to automatically find cancellations in the structural parameters of your physical systems, which, if holds, then enhance dissipation. Okay, for those of you who are a bit in the literature, the Timoshenko system, you will know that if the parameters satisfy a certain equality, then the decay of the energy is actually exponential and not just polynomial. Okay, and this is we're able to show this And we're able to do this for any system you give me. I'm able to give you the conditions on the parameters such that you can enhance dissipations, okay, which is quite cool if you ask me. And all right, so final, yes, you can send me an email if you want to discuss more on this final detail. So final, let's say, what will be the next level, okay? So for next work, we want to study the optimality of the algorithm. And then we also want to see if we can extend it to more complicated settings, like for instance, when A is asymmetric or when you have a parabolic dissipation too, okay? So in this case, you will have 4 terms. So you will have different ways of matching the scalar products, but everything should work the same, okay? And yeah. So with this, I conclude my talk, and thank you for the attention.
Thank you, Professor Liverani, for your excellent talk. Now, question, any question or commentary? This video and audio is open for question.
Please. Good afternoon, Dr. Limaco. I would like to send a question.
I can hear you. Yes.
I would like to know the theorems about the nonlinear hyperbolic equation. Are there solutions for this problem?
So, no, this is actually something that we would like to. I should add it also here to the next level. Something that we want to study because, of course, there are several techniques, of course, as I said, to show that the energy decays, okay? But the Lyapunov functional one is very useful to deal with nonlinear problems, right? Because if the nonlinearity is good enough, then you can hope to obtain a certain decay of the energy. And but we didn't explore that case. So the most we can do is that if you have a nonlinear system, you can linearize, and then you can study around the equilibrium, and usually you obtain something like this. Okay, but no, we currently don't have results on this.
Thank you, Hernan. Any question or commentary, please?
Dr. Limaco, you would like to ask one more question?
Yes, Hernan, please.
For the second order equation, is possible the solution or similar?
Yes, for sure. If you have a second order equation, you can simply rewrite it as first order, okay? And usually what happens is that, so for instance, let me go here. So this equation here, this system here, actually is the wave equation with weak damping, okay? The reason is that if you take the derivative, the time derivative of the first equation, and you substitute u2 xt, you will find that this is precisely the wave equation with weak damping, okay? So usually what happens is that if you have a second order hyperbolic differential equation, you can rewrite it as first order, and then you can find a suitable transformation of the variables such that you can write it down in our setting, okay? And then you can just use all of the machinery I just discussed and show the decay of the energy, yeah.
Thank you.
Thank you very much. Thank you very much, Professor. Thank you very much, Professor Limaco.
Other question? Any question or commentary? Please. If no more questions, thank you again, Professor Lorenzo Liverani, for your excellent talk. Thank you very much.
I will stop sharing.